Okay, here's the last bit that we're going to go over. This is the kinetics and the rates of reactions. So before, in the previous chapter, when we were talking about Gibbs free energy thermodynamics, we talked about favorable and non-favorable reactions, right? So favorable reactions are reactions that are spontaneous, okay, and they can proceed um, without influence, right? Without any influence. All right. These types of reactions, just to review, favor products, right? They go into the direction of the products because they tend to move forward. Then you have non-favorable reactions, right? Thermodynamically favorable or non-favorable reactions. And when you see non-favorable reaction, what you're talking about is a non-spontaneous reaction, right? This will not proceed without outside influence. And these types of reactions tend to favor the reactants, right? So this goes into the direction of the reactants. Okay. Um, so looking at the reaction above, right? Whether it's spontaneous or non-spontaneous, right? Reactions occur at different speeds, right? Now, even though a spontaneous reaction can proceed forward without any outside influence, those can be as quick as a combustion as we see here in the reaction above, or it can be as slow as iron rusting over the course of several weeks, right? The fact that it's proceeding forward has no bearing on the rate or the speed at which it moves forward, right? So what we're going to learn about right now is we're going to learn about the factors and the things that affect the rate at which reactions move forward. So let's take a look at this one right here, right? So if you take a look at the combustion that occurs here, right? What we're seeing is two reactants coming together and forming two separate products. Okay, just make a quick correction here. Okay, so what's happening here, right, is that we have propane, which is C3H8, reacting with oxygen. Now, when you look at this reaction, right, this is giving you an overall picture of what's happening, right? That's not to say, right, that this happens instantaneously, right? So there's lots of factors that affect the rate of a reaction, and we need to understand that this doesn't happen instantly, right? So remember, when this reaction occurs, you have a propane molecule, which looks like CCC, and then you have carbon or hydrogen surrounding these, right? Okay, so what this reaction is telling you, right, is that this one propane molecule is going to come in contact with two O2 molecules, or five, sorry, at this exact same time, right, and create this reaction instantly, right? That's not how this works. Okay, so we have to understand that reactions like this, even though this is painting an overall picture, right, of what happens to create these two products, it's not like these things come together instantly. It happens in steps, right? The steps that dictate a reaction is called a mechanism. So you're going to see that word a lot. So the mechanism, right, are the steps that occur within a reaction. Okay, we're going to learn about mechanisms a little bit later, but because a reaction does occur in steps like this, then there's different factors that affect the rate at which a reaction moves forward, right? So let's take a look at a factor that affects a reaction, right? A reaction going forward. First one is going to be the nature of the reactants, right? Some reactants are going to be much more reactive than others, right? And their reactivity is going to dictate how fast the reaction moves forward, right? So basically what we're looking at is chemical reactivity of the reactants, right? Like if you look at something like sodium, right? Sodium is gonna react almost instantly when taken out of the oil, right? It's gonna react to tarnish because sodium releases electrons really easy, right? And it's a group 1 element. So anything that's really bonding with sodium or reacting with sodium with pure sodium is gonna be pretty fast, right? But then you look something like iron, right, which is exactly the example that I used earlier. Iron is going to react with the air around it the same as sodium, but in order to form a reaction to form like rust, for example, which is iron oxide, right? This moves a lot slower than sodium does. Sodium reacts within seconds, and the creation of rust can take anywhere from a few days to a few weeks, depending on how much the exposure it has to the air. So the nature of the reactant is going to play a direct role in how fast a reaction moves forward, right? Let's take a look at another example. The another example would be the ability for reactants to meet. Remember, in order for a reaction to move forward, the reactants have to come in contact, right? So if the reaction has two or more reactants, right, they have to be able to come in contact with each other. This is one of those things that reactions are often carried in solutions, like aqueous solutions, or in air, like in gas state, because if you have something that's in a gas state, right, let me see, often reactions, so write this down, reactions happen in solution or in gas state, right? For this reason is that this is why the reactions move forward a little bit faster, because if you have individual molecules that are able to move freely in solution or in a gas state, they're going to have more ability for them to come in contact with the other molecules and create that reaction. But if you combine two salts in solid state, right, then you have just two crystals that are kind of rubbing up against each other, and you're only getting that one point of contact. So if you have like a solid that here reacting with another solid here, you're only seeing contact in this area here, right? So you're not getting a whole lot of interaction between the molecules, and even that whatever interaction you do, it's very minimal. Now, if you have molecules that are floating around in solution, right, and you have another molecule that's in there intermingling with other individual molecules, you're going to have much more interaction, and you're going to have a better ability for the reaction to move forward, right? So you want to see that these reactants are able to come in contact and react with each other, right? And we also talk about like heterogeneous and homogeneous reactions. If you have reactants that are in different states, for example, let's say you have a pool of gasoline, right? And you set it afire, right? So let's say it's got a little fire going here. Well, the only part of the gasoline that's making contact with the flame is whatever part of the surface of the puddle that's coming in contact with the air to make that combustion reaction, right? Now, if you take the same gasoline, right, and you vaporize it like you do like in the intake of a car, right? Because like I work on cars and I do old school carburetors. The carburetor vaporizes the gasoline and turns it into individual little droplets. Those droplets are going to have way easier access to intermingle with the air and create a much faster and cleaner burn than it would be just a puddle of gasoline, right? So things like that have an effect on the ability for reactions to move forward. The other thing that we can look at is the concentration of reactants, right? If you have a high concentration of reactants, meaning that you have a lot of stuff to work with, right, then you're going to have a much more interaction between reactants. But if you only have a few droplets of that gasoline with an overabundance of air, you're not going to have a whole lot of reaction, because there's not a whole lot there for you to work with. So the concentration of reactants also plays a huge role. The next thing that affects too is the temperature of the system, right? Reactions tend to happen faster at higher temperature. And the reason that this happens is because if you increase the temperature, you're increasing the kinetic energy. Increasing the kinetic energy means you have greater chance of collision. And the more collisions you have, the greater amount of of a reaction that you're going to occur, right? So if these, for example, if these gas particles are moving a lot faster because it's higher temperature, they're going to collide with the oxygen molecules a lot easier, and you're going to have a much faster reaction. And the last thing that we're going to take a look at is going to be the presence of a catalyst. Right, so this is something that one of you had mentioned. You had never seen this. So a catalyst is basically any substance that increases the rate of chemical reactions without being used up, without reacting itself. So this speeds up a reaction without actually reacting. And we'll see a little bit how catalysts have an effect on a chemical reaction, right? So let's take a look at what we're talking about when we're talking about rates of reactions, right? So here we have a graph, right? We have a simple graph here that has the reaction of hydrogen iodide decomposing, right? This is in gas, decomposing to hydrogen gas and to iodine gas. Okay. Now, what we're looking at here is the rate of the composition of the reaction. It's basically, if you can see, it's a curve, right? And we have different time points at which we take this measurement. Now, across the side here, we have the concentration that's expressed by the HI in the brackets, and then across the bottom, we have our time. Now, the rate of reaction is pretty much the same thing as anything, like as what you're getting paid, for example, right? You're getting paid, $15 per hour. That's the rate at which you're working, right? And how do you write that? How do you write $15 per hour, right? You're basically just saying that you're getting $15 for every 1 hour that you work, right? So when you say per, what you're implying is a division, right? You're getting $15 per every 1 hour that you work. And concentration is pretty much the same thing, or I'm sorry, reactions pretty much work the same way. A reaction is expressed as the concentration of the reactants, right? The reaction rate is the concentration over time. Right? The concentration over time. And if you look at our graph, that's exactly what we have. We have concentration over time. Now, in our annotations here, right, remember that molarity or concentration is expressed as the molar concentration, right, of whatever you're working, and that's going to be over a unit of time. Now, remember that molarity is expressed in moles per liters per seconds, right? If you do it as a rate. So you can see this expressed as moles per liters over seconds, but most commonly you're going to see that it's going to be written as moles, liters minus 1, seconds minus 1. Remember that the negative exponent just means that both of these units belong in the denominator of that fraction, right? Because at its heart, a rate is a fraction. So let's take a look at our graph. So here we have our starting concentration here and our ending concentration over here, and then we have several points. Now, this curve, right, represents the rate of decomposition, or represents the decomposition or the decrease in the concentration of hydrogen, right? And then to find the rate at which this happens, right, the rate can be written as the slope of this curve. So the rate is equal to the slope of the tangent line of this curve, right? This is the same thing in calculus for those of you that have done calculus. Remember that the tangent line is equal to the rate, which is equal to the the derivative? The derivative of a line, right, of a function, is the slope of the tangent line in a line, in a graph. So if we take a look at this curve, right, you can see here that the tangent line has been drawn on this particular curve, right? So the tangent line is drawn to this point here. Now, if we take a look at this function, right, and we draw this line, and we can calculate the slope of this line, remember that slope is equal to change in x, change in y over change in x, right? And to simplify this, it's basically just rise over run. All right, so if we take a look at this, you can see if you put a dot here on this line, right? Because the point slope formula says that, and you put a dot here at this time interval, right here. The difference from here, let's call this 0.67, and we'll call this point here 0.040. If you take that difference, right, which is 0.067 minus 0.040, you end up with this amount here, which is the 0.027, right? So the change in the y-axis is represented by that 0.27, and then you can see here that the difference between, let me get a different color here, between here and here is labeled at 110 seconds, right? So if you take the rate, right, which is shown here, of 0.27 moles per liter change in concentration divided by the time, then you're going to end up with a rate of 0.00025 moles over liters, or moles per liter seconds negative 1, right? This is exactly the same thing, just written in scientific notation, but that's basically it. What this calculation is showing you is that if you're given a curve, and you pick a point on that curve, you draw the tangent line, the slope of that line is going to give you the rate of the reaction, okay? It's pretty simple. This is, basic algebra 1, because remember that a line is just equal to y is equal to mx plus b, right? And to find this, they took the point slope formula, which is, y2 minus y1 over x2 minus x1, right? It's pretty much it. Okay, so take a second, absorb this, and then we'll go ahead and continue with this. Okay, so we're going to move on here a little bit. We're going to talk about these tables in just a minute. But let's take a look at something real quick, right? So that's concentration, right? I mean, that's, basically concentration in the rate. But there's an equation called the rate law that expresses the way concentrations of reactants affect the rate of a reaction. So let's assume, right, that a reaction is very simple, and we just have reactant A plus reactant B react to produce some set of products. All right. Now, the rate of the reaction, right, can be written as follows, right? If you take the rate, right, of the reaction, that's going to be proportional to the molar concentration of reactant A times the molar concentration of reactant B. All right. Now, if we introduce something, right, that would help dispel this proportionality, we can actually replace that with an equal sign if we introduce something called the rate constant, which is represented by the letter K. So if you have the rate constant, right, then the rate constant is equal to the molar concentration of A times the molar concentration of B, right? And that's basically our rate law, right? It's basically our rate law. Now, N and M must be determined experimentally. Okay, it must be determined experimentally. So let's take a look at a reaction, right? Let's take a look at a reaction. Let's say we have a reaction that has H2SeO3, which is selenic acid, plus 6I, which is iodine, plus 4 moles of hydrogen, right, to produce selenium plus iodine plus water. Okay, so if we were to write this rate law for this reaction, right, this is what it would look like. It would look like the rate is equal to the rate constant times the molar concentration of the selenic acid, which is H2SeO3. Okay, that's going to be raised to the power of X. And then we're going to have iodine, and then finally hydrogen. This is going to be to the Y, and this is going to be to the Z. Okay? Now, after the experiment has been done, it was determined that the X has a value of 1, the Y has a value of 3, and the Z has a value of 2. So if we were to write this rate law, right, with the correct exponents now, then the rate law would look like this. The rate would equal molar concentration of the selenic acid to the 1, iodine to the 3, and hydrogen squared, right, times K. With me so far? Now, if the value for K is equal to 5.0 times 10 to the 5, liters 5, moles negative 5, seconds negative 1, right? That's the rate constant for this reaction. Let's plug it in and see what we get. Okay, so let's do the solution. Let's say that we wanted to know what the rate of reaction at 0 degrees when the concentrations for this reaction are as follows. So I have the concentration of selenic acid at 2.0 times 10 to the negative 2. All right, molar. Iodine is at 2.0 times 10 to the negative 3 molar. And then finally, hydrogen is at a concentration of 1.0 times 10 to the negative 3 molar. Okay, so we have our reactant, we have our rate constant, which is here. So what we're going to do now, we're just going to plug everything in, right? So let's calculate the rate. The rate is going to be equal to 5.0 times 10 to the 5th liters 5, right, over moles 5, moles to the 5th, times seconds, okay? And then we're going to multiply that. We're going to multiply that by 2.0 times 10 to the negative 2, right, moles over liters. We're going to multiply that by 2.0 times 10 to the negative 3 moles over 1 liter. And then we're going to multiply that by 1.0 times 10 to the negative 3 moles over liters, right? This is going to be cubed. Sorry, this is going to be squared. This is going to be cubed. Remember that this is the H2SeO3. This is the iodine, and this is the hydrogen, right? Okay. So basically what's going to happen, right, is we're going to simplify this, right? We're going to simplify this, and we're going to end up with all right. Okay. When this one, the first one, the selenic acid is going to stay exactly the same, right? It's going to be 2.0 times 10 to the negative 2 moles per liter, right? Because it's to the first power. So that's not going to change. When we cube this one, we're going to end up with 8.0 times 10 to the negative 9. But now moles are going to be cubed, and then liters are going to be cubed. All right. And then finally, when we square the last one, right, which is the hydrogen, we're going to end up with 1.0 times 10 to the negative 6. This is going to be moles 2 over liters squared. All right. Now, what happens here, right, is these moles, let's cancel the moles first, right? So remember, there's 5 moles here. So this one's going to cancel 1. That's going to leave you with 4. Then you're going to cancel, let's see here. You're going to cancel 3 more. So now you're at squared. No, you're going to be left with 1. Sorry. Right? I had to double check myself there. So the first one here, you're going to cancel, right? So look, let's do it like this to make it a little bit easier for you to see. There's 5 moles to begin with. 4, 5. Okay, so these first one's going to cancel the first mole. This one's going to cancel the next 3, right? And then the last 2 is going to cancel the 1 here, and you're going to be left with 1 mole up here, right? Okay. Same thing. Let's do the liters. This one's going to cancel 1. This one's going to cancel 2 more, and then you're going to be left with 1 liter at the end. So when you multiply all this out, right, you're going to be left with 8.0 times 10 to the negative 11, the 1 mole that's left over the 1 liter that's left over from here. So then your rate is going to be equal to 8.0 times 10 to the negative 11 moles times liters negative 1 times seconds negative 1, right? And that's going to be the rate for this reaction, okay? Now, I want you to take a look at something, right? Because we've been doing equilibrium for the last couple of weeks, right? And I want you to look at the rate law that we wrote for this one, okay? I want you to pay particular attention to the exponents, right? You're asking, well, why aren't the exponents 1, 6, and 4, right? 1, 6, and 4, because every time we do an equilibrium, right, the m and the n, or the x, y, and z, are always replaced with the coefficients. So understand that this is a rate law, okay? And these numbers here have to be determined experimentally. If the exponents and the rate law exponents here, right? I mean, if the coefficients and the rate law exponents happen to be the same, that is coincidental, okay? That doesn't mean that the coefficients of the reaction are going to be the exponents you put into your rate law. Those have to be determined experimentally. So oftentimes these numbers here are not going to match the coefficients in a rate law, because that has to be determined experimentally. And that's what we're going to figure out next. How do we determine the exponents of a rate law, right? If you can't use the coefficients from the balanced equation. Okay, so now we're going to move back up to these graphs over here. Okay, and I'm going to scooch over this way, and we're going to take a look. So remember that the rate law of a reaction, right? So the rate of a reaction is equal to the rate constant times the molar concentration of reactant A, N, times the molar concentration of reactant B to the M. All right, so let's take a look at a couple things. Okay, so here we have experimental data, right? In this table right here, table 18.2, we have experimental data. We have the initial concentrations of reactant A with initial concentrations of reactant B, right? And then here we have the initial rate of formation of products, meaning how many products are being formed as a result, okay? So let's take a look at this, and let's figure out what happens. All right, so if we take a look at reactant A, let's take a look at that one initially, because you can see in reactant B, there's no change for the first 3. Do you see that? There's no change here. So we're going to take a look at reactant A. Now, from the first 2 data points, right, we see that the concentration of reactant A changed from 0.10 to 0.20, right? We see that here and here, right? So what's happening here is that we're seeing an increase in the concentration of 2. So it's increasing 2 times. Do you see that? All right. So now let's take a look at the products. And you can see that when the concentration of reactant A increased, right, or doubled, we saw a doubling of product formation, right? Because if you take 40 and divide it by 2, you basically get 20, right? I mean, you get 2. So we see a doubling, right, in the reactant of A, and then we see a doubling in the reactant of in the formation of products. So what we're seeing here is a one-to-one change, right? Because you're seeing a doubling of one and a doubling of the other. So that to me tells me that it's a one-to-one, right? So if one doubles, the other one doubles, you know? So let's take a look at our reactants. So what we see here is this. When the concentration of reactant A is equal to 0.10, then the product formation, or is equal to 0.010, right? Which is noted as A prime. When the concentration of reactant A becomes 0.20, which is a doubling of reactant A, right? Then we see that reactant A prime also becomes 0.20, right? So as one doubles, as a result, the other doubles. So let's take a look at graph number 2. Here's what we're seeing, right? We're seeing that if the reaction in reactant A, the concentration doubles, and we're getting a doubling in the product, then we have a one ratio, right? Because if this one doubles, right, and then the other doubles as a result, then the exponent that would make that true would be a 1, right? Because 2 is equal to 2 to the first power, which is 2, right? So then the exponent that goes on reactant A then becomes a 1. So now we just realize that N is equal to 1, right? It'll make more sense as we go through the next example. All right, so let's take a look at reactant B, right? Now, in this case, you see that there's no change in reactant A, but there is a change in reactant B, right? So here we see the same doubling effect. We see that 0.1 becomes 0.2. So this is a doubling effect, right? Let's take a look at the formation of product and see what happens here. So if we take 2.40 and we divide that by 0.60, here's what we get. We get an increase of 4-fold, right? So this here is an increase of 4. It increased 4 times, right? So what's going on here is this. What we're seeing here, right, is a 4-fold increase. So let's take a look at our table. We saw that the concentration of B is doubled, right? But in the product formation, we see that we had a 4-fold increase. In order for that to be true, then you have to square that value, right? So 2, when the reaction initial concentration is doubled, we see a 4-fold increase. In order for that to happen, you need to take that same 2 and you need to square it, right? You need to square it. So what we're seeing here is we have a reaction to the second order, or exponent 2, right? Let me give you an example of what I'm talking about to kind of simplify this. Let's say that reactant B had initial concentration of 0.3, right? And then the product formation, we see that B prime now has a 0.09 or a 0.9, right? 0.09, right? So the concentration, basically what's going on here is that it increased that twofold. Okay, so let me see. I might have got a little ahead of myself. Let's try this again. So B is equal to 0.03, right? That's the initial concentration. Now, if you take that and you square it, you're going to end up with 0.09, right? Okay. Now, if I double the concentration of reactant B to 0.6, then B squared of that is equal to 0.36. Now, if I take 0.36 and I divide that by 0.09, then you get a factor of 4, right? So what this is showing you is this, right? If you double the reactants, right? This is double the reactant, right? I'm going to just abbreviate with R. If you double the reactant and you see a 4-fold increase in the product, then in order for that to be true, then this reactant has to be squared, right? So what we found here is that M is equal to 2. So if we were to write this reaction rate, right, and we're looking for the rate constant, then I'm going to rearrange my formula. So the rate constant is equal to the rate divided by A times molar concentration of B squared, right? Now, let's just go ahead and pick one, right? So let's go ahead and pick up a rate, right? And let's see here, we'll pick this one here, right? Just that's the initial one, right? So we're going to say that K is then equal to 0.20, right? Moles, liters minus 1, seconds minus 1. Then I'm going to divide that by the molar concentration, 0.10 moles, liters minus 1, times 0.10 moles per liters minus 1. Then I'm going to square that. Now, where did I get these concentrations from? I got them from the data, right? Because this is done experimentally. So here's the initial concentration for A. Here's the initial concentration at B at this rate, okay? We figured out, based on the increase that we saw here and here, that the exponents for each one of these is going to be a 1 and a 2. So that's what we did here, right? So if we simplify this further, we're going to end up with 0.20 right? Moles, liters minus 1, seconds minus 1, all over moles 3 times liters negative 3. All right. And if we divide that out, cancel our units, our rate constant is going to be 2.0 times 10 to the 2 liters 2 moles negative 2 seconds negative 1. So the rate constant for this particular reaction based on the data is 2.0 times 10 to the second liters squared over moles squared seconds, right? Now, the tricky part was figuring out what the exponents are going to be for this particular reaction, right? So let's take a look at this table a little bit further and let's see exactly if we can figure out what's going on here, right? So these numbers here, right, represent the change of the initial concentration, right, or the concentration that was changed, right, in the reaction. This number here represents the amount of product that was formed, and then this number over here represents by the factor at which it changed, right? So for example, let's say we have a molar concentration, and we'll make it simple, right? Let's say we have a molar concentration of 4, right? And then we see that 4 times as many, right, products were formed. So in order for that to be true, then you would have to square that 4, right, to get to the 16, right? So this one would mean that if you see this change in reaction with this many products, then that would be an exponent of 2. All right, so let's take a look at what we see here. Let's say we have an initial concentration of 2, right? Or we see a change in the concentration double, right? Let's say it doubled. That's what this means. I'm sorry. It doubled. Now, as a result of this doubling, we see that the products increase by 3-fold, right? Because let me see here. Because to get here, you would have to take 2 times 2 times 2 to get to 8, right? So because if you see a doubling in the reaction, right? But then you see a threefold increase in your products, then the exponent that goes here is a 3, which means you have a third order reaction, right? And we'll get to what the order of reactions are in just a minute, right? The same thing happens here, right? Let's say you have a tripling in the concentration of the reactant, but you get this amount of product. That means that in order for you to get there, you had to do 3 times 3 times 3, which is 9 times 3, which is 27. So then that would also receive an exponent of 3. So looking at data is going to be the only way for you to really be able to determine the amount or the exponent for the reactant, right? So let's take a look at an example question. I'll move down here to the bottom, right? Let's say I have a reaction, right? That looks like this. I have SO2Cl2 gas, right? That produces sulfur dioxide, right? And chlorine. Okay. So we can see here that this is going to be a homogeneous reaction because everything is in the gas state, right? So let's take a look at our initial concentrations, right? Let's take a look at our initial concentrations of this one. So we have 0.100, we have 0.200, right? This is all moles per liter, don't forget, 0.300. Now, the reaction rate that we're seeing here is going to be 2.2 times 10 to the negative 6. We're going to have 4.4 times 10 to the negative 6. And then we're going to have 6.6 times 10 to the negative 6. Okay. Here also is going to be moles per liter seconds because it's a rate. Okay. So let's take a look. So if we see here, right, that we see a doubling, this doubled, right? In the amount of the reactant, right? So we see that the initial concentration or the change in the concentration doubled. And if we take a look at our rate, we see that the rate also doubled, right? So because the rate also doubled, then I can see that this is a 1-to-1. So in order for this to be true, if it doubles and I get a doubling effect in the rate, then the exponent that would make that true would be a 1. Right? So because the exponent in this case is a 1, then we can write our rate law, right? So K is equal to the rate divided by the molar concentration of, and that's going to be to the 1. So if I wanted to find the rate constant for this reaction, I would just pick a value, right? Let's do this one, the first one. Why not? We'll do 2.2, right, times 10 to the negative 6. This is going to be moles, liters minus 1, seconds minus 1, over the initial concentration, which was 0.1. That's going to be to the 1, and this unit is going to be moles, liters minus 1. Okay, so let's figure out what cancels. That's going to cancel here, here, and I'm going to be left with 2.2 times 10 to the negative 5 seconds minus 1. And this is going to be equal to K, right? So using the data, right, we're able to determine what exponents we're going to use in our rate law, okay? I'll go ahead and leave you guys one question to work on, and let's see if you guys can figure it out, okay? So I have the following reaction, which is 2NO. This is also in gas, plus 2H2, which is also a gas. Now, something else that I want you to notice that we're only using the reactants with the rate law because the disappearance of the reactants, right, is basically what's giving us the rate at which the reaction happens, right? The change in the concentration of the reactants and then the change in the concentration of the products. But in the rate law, we only use the reactants. So let's say that we have our initial concentration for nitrogen monoxide and then hydrogen gas. right? So here we have 0.10, 0.10, 0.20, and then for hydrogen we have 0.10, 0.20, and then 0.10. All right. So the rates for this are going to be as follows. Okay, it's going to be 1.23 times 10 to the negative 3. It's going to be 2.46 times 10 to the negative 3. And it's going to be 4.92 times 10 to the negative 3. Okay, go ahead and write this problem down. And basically, I just want you to write the rate law reaction. You don't have to calculate it, but you could. Just see if you can figure this one out. Okay, I'll go ahead and stop the video for now, and then we'll move on to the next bit in just a bit. If you have any questions, just reach out. Let me know. Basically, all we're doing here is, remember, determining the order of the reaction, and that's going to be determined here. The exponents tell you that whether it's 0 order, 1st order, 2nd order, or 3rd order, and we'll get more into those details as we go along.